It's time for fun with math, and today we're going to talk about transformations and symmetry. Mostly in this video, we're going to focus on transformations. So the idea of a transformation, it's actually pretty simple. Here's a graph. You can transform this graph another way, in a number of ways. So you could go to the right, you could move it to the left, you can move it up, you can move it down. You can make it smaller, you can make it bigger, you can even spin it. These are all examples of transformations of this graph. We'll talk about some simple transformations today, horizontal and vertical shifts, stretches and shrinks, and then some reflections. But first, I want to talk about just some basic graphs and formulas you should be familiar with, in case that you're not. Because the idea really is you start with these sort of basic graphs and formulas, and then you can apply these transformations to get new graphs and new formulas. So let's take a look at an example here. So here are some of the basic graphs and formulas you should be familiar with. And if you're not, it's okay, but we need to familiarize you with it. And you always have your graphing calculator to kind of help you a little bit. So let's take a look at these. All right, so some of these should be pretty obvious, like over here, here's f. F is the nice looking line, y equal x. So when we come over here to label for part F, this should just be the line x. And then above it, this one's not so bad too. This one, most of you guys know, this is the parabola, the function y equal x squared. So over here for part B, we could label this as x squared. And then D sort of completes this sequence of graphs. Part D is actually the graph y equals, well, you have x to the first power, x to the second power. You can kind of guess this is actually x to the third power, so it's x cubed. And so D is x cubed. These are the only graphs you really need to be familiar with nice powers of x. Because if you wanted to look at a graph, let's suppose you wanted to look at something like f of x equal to x to the fourth. Well, oops, so x to the fourth here. So if you want to look at x to the fourth, what its graph's going to look like, it's basically going to look like x squared. It's just going to be a little bit more narrow here because it's going to go up faster. So it look basically like this, but it'll just go up faster. And the same thing for f of x to x to the fifth. So if you have any odd power of x, it's going to basically look like x cubed. It's just going to go up faster. So it'll go up faster here, and it'll go sort of down faster there. And that's the idea. So any even power looks kind of like x squared. Any odd power kind of looks like x cubed. All right, so that's for the nice powers of x. But what about the negative powers of x? So if you look at this one here, part C, this is actually y equal to, if you want, we could write this as x to the negative 1, but typically we write it as 1 over x. So over here for part C, that's x to the negative 1, or more typically we write this as 1 over x. And this is basically what any negative odd power will look like. So if you want to look at something like f of x is equal to x to the negative 3, which is really 1 over x cubed, it's basically going to look like this function, but it's going to be a little bit lower. It's going to be a little bit below this one in black here. Now, I didn't talk about the negative even powers of x, but if we look at that function, just for fun, if you look at this function, x to the negative 2, which is really 1 over x squared, it basically looks like 1 over x. The only difference here, it does a similar thing, but on this side, instead of being negative, it's actually positive because you're squaring it. So it looks something like that. All right, so we have the negative powers of x and the positive powers of x, the nice ones at least. What about fractional powers? So if we come down here to G, you may be familiar with this little graph here. This is actually the graph of square root of x. Or if you like, you could write this as x to the 1 half. So G right here is actually x to the 1 half, which is actually the square root of x. And so that's x to the 1 half. And if you had to guess, to kind of set this up for you, this is x to the 1 half. I bet this one would be x not to the 1 half, but to the 1 third. And it is. This is actually the cube root of x. This is maybe the one that you weren't so familiar with. It's the cube root of x. And so that's e. And so here you could write x to the 1 third, or we could write this as the cube root of x. And of course, any even root, so if you have any even root, like you wanted to say, hey, what is the fourth root going to look like? Basically, the fourth root of x, which is really x to the 1/4, is going to look the same as the square root of x. It's just actually going to fall a little bit lower than the square root of x. So it might look something like this. And of course, any odd root, so say the fifth root of x, it's going to look basically like the cube root of x, except it'll lie a little bit lower. So it might do something like this, and come down and do something like that. It's just going to lie a little bit below the cube root, but it has the same sort of shape and form, and that's what we want. We want to understand the shapes, and we can use those when we couple them with transformations later on. All right, we have one more to do, part A. So part A is part of a special sort of formula. It looks like the letter V, and this one is just the absolute value of x. So these are some of the graphs that you should be familiar with, and if you're not, you should familiarize yourself with them, and then make sure you can always find them on with your graphing calculator if you don't know them until you have them kind of memorized. All right, let's move on. Because what we really want to talk about today is transformations. And we're going to look at basically 5 or 4 different types of transformations. So we're going to look at shifts, stretches, and shrinks, and we'll do them both vertically and horizontally. And then we're going to look at reflections. And there's a reflection across the x-axis and the y-axis. So I guess basically 4 transformations, right? Shifts, stretches, shrinks, and reflections. It's a very simple idea. So we're just going to kind of do this little example together to get a feel for what's going on. So the idea is I give you a graph here, and we want to try some shift transformations. And we want to shift vertically up 2 units. And so what we're going to do is we're just going to pick a couple points. This will be one point we pick, one at the origin. And of course, if you shift it up 2 units, it's going to go up here to number 2. So right here, we'll just put that red dot at 2. And of course, we'll pick some other dots, some other nice points, like this point right here. If you shift it up vertically 2, it's going to go right there. So over here, we'll put that blue dot right there. And then we'll take one more dot. Let's take this one here. And we'll shift it up 2, and so it'll go right here. And then all we basically have to do is connect the dots. And you can visualize this sort of in your head, but I mean, that's the idea. So you just connect the dots the best you can. It doesn't have to be perfect. Right, we're just getting a feel for what's happening here. This tool is hard to draw with it. There we go. All right, so this was the formula f of x. And so when we shifted it up 2, what happened? Right, we didn't change the horizontal stuff. You didn't change the x stuff. You just changed the y stuff, the vertical stuff. So for the formula, the outputs, just you added 2 because you shifted up 2. So there's the new formula, f of x plus 2, that will give you this graph right here. Let's look at the next question, which instead of shifting up, you're going to shift down. And basically the same thing's going to happen. You have this little red dot here, so instead of going up, you're going to go down here. Then you have this little blue dot over here. Instead of going up, you're going to go down 2, so you're going to wind up right here. And then you have this little green dot right here. And so that winds up right there. And we're going to simply connect these 2 or these 3 dots. So you connect this with a line, so it goes down. You connect this with a line. And what you want to realize is that the inputs never actually changed. All the inputs stayed the same. Right, the green input is 1, the green input's still 1. The blue input was -1, the blue input's still -1. The only thing that really changed were the outputs. So what that means is you're not working on the inside of the function, because you're not working with the inputs. You're working on the outside of the function. So you just subtract 2 from the outside of the function, as you're working on the outputs. All right, so working with outputs is actually pretty easy. Now, working with inputs is not as easy, and the reason for that is you have to kind of think everything's the opposite of what you think. But first, let's do the transformation with the graph, because it's actually pretty easy to do. So now we want to shift horizontally to the left 2 units. So this one's going to go to the left, 1, 2. So I'm going to move right here. And then that little blue point we had right here, it's going to go to the left, 1, 2. So it's going to wind up right there. And the little green point we put right here, it's going to go 1, 2. It's going to wind up where the blue point was. And of course, we just connect the dots. And so we just connect these dots right here the best we can. All right, so you can see how the graph was actually shifted to the left 2 units. Now, here's where the question comes. Did you work with the inputs or the outputs? Did you change the x stuff or the y stuff? What you'll notice is that the outputs actually never change. They're still the same. The blue output here is -2. The blue output here is -2. What happens is you change the inputs. And what that means is you're not going to work on the outside of the function. You're going to work on the inside because you changed the inputs again. So here, what happened is you move this to the left 2. And so when you move the inputs to the left 2, it's always the opposite of what you think when you work on the outside. So you want to say -2 because that's what it means to go to the left. You know, if you go to the left, you want to think it's subtract 2. But it's not because you're on the inside. It's the opposite. So you actually are adding 2. All right, so the rule is basically when you're working on the outside, everything is fine. Right? You're like, this is great. I'm in a very happy mood. If I add 2 vertically, I just add 2 to the outside. If I subtract 2 vertically, I subtract 2 from the outside. But when you're working with the inside, when you're working with the horizontal stuff, with the x stuff, I'm very unhappy because it does the opposite of what I think it's going to do. Right? So in this case, I thought I would subtract 2 because it went to the left 2, but it doesn't. It adds 2. And you can even check this. Right? So how can you check this? Well, you know, for this function, if you plug in -2, you have to get out 0. Right? So what happens when you plug in -2 into this function? Well, you get f of -2 plus 2, which equals f of 0. And of course, this is your function f of x over here. And you can see if you plug in 0, you get out 0. Oh, so it matches up. If you thought incorrectly, if you believe that this was f of x minus 2, well, when you try to check it, it says when you plug in -2, you get out 0. So you plug in -2. So f of -2, and you have a minus 2, which would be f of -4. And so you come over here to find f of -4, which you can't even see. So here's -4. So somewhere down here, there's a point, but clearly that height is not 0. Right? So this is not equal to 0. I don't know what it is, but it's not equal to 0. I can see that. So you can see you made the wrong choice. Right? You thought it was -2 because you thought you were, going to the left, but you're working with the inside. So it's always the opposite of what you think. So it's +2. Let's do another one to practice this. So let's now shift horizontally, but not to the left, but to the right. And so here we can draw this. It's pretty easy. Just 1, 2 to the right. So you go right here. And then let's take that blue point over here and move it to the right too. 1, 2. So it's wind up where the green point is going to be. And then that green point, let's move it to the right too. So you move it to the right too, and you wind up right here. And so it's easy. Everybody understands, oh, that's what it means to shift to the right too. You can draw it. We can draw it. Something like that. And then when we go to write the formula, you have to think to yourself, okay, so did we work with the inside or the outside? Did we do horizontal or vertical? Well, horizontal. The vertical stuff remained exactly the same. The red's heights are the same, the blue heights are the same, the green heights. So we're not going to work with the outside, we're going to work with the inside. And when you work with the inside, remember this is your original function of x, you do the opposite of what you think. So I have x, I want to say I add 2, but it's the opposite, so I subtract 2. And so there's the formula for that transformation. All right, let's continue on, let's keep working with this, but remember the rule, if you work with the outside, everything's sort of fine, you're happy. If you work with the inside, you're a little unhappy because it's the opposite of what you think to do. So let's look at some stretches now. So here we're going to have a stretch vertically by a factor of 2. So remember, this is our original function here, f of x. And we're just going to take our points. And the first point we're going to pick, of course, is at the origin. Now here, the output is 0. So what happens when you multiply 0 by 2? It goes nowhere. So when you try to stretch this vertically by a factor of 2, it just stays where it's at. And then we're going to take this point right here. I'm going to stretch it vertically by a factor of 2. So basically, vertically it's -2. So basically we'll multiply by 2 and go to -4. And so you basically, the idea is you're just pulling this stuff down. And so you go right here. And then we take this green point right here. And it has height -2. So we'll multiply that by 2 because we'll stretch it vertically by a factor of 2. And it'll go to -4 too. So you can see the idea. What does it mean to stretch vertically by a factor of 2? You're just kind of pulling this function sort of down by a factor of 2, and so it's getting a little bit more narrow. And so that's what we mean by a stretch vertically by a factor of 2. And so then you ask yourself, did you change the inputs or the outputs? And what you'll notice is that the blue input's the same here, the green inputs are the same, the red inputs are the same. The only thing that really changed are the outputs, because this blue output was -2, and this blue output is -4. So you're not going to work on the inside, you're going to work on the outside, because you changed the outputs, which means it's going to work just like you want it to work. So stretch vertically by a factor of 4, so factor of means just to multiply, so we just multiply it by 2. Because that's exactly what you're doing here, just multiplying the heights by 2. So there's our formula for that transformation, 2 times f of x. Now here we come with the stretch, but instead of vertically, we're going to go horizontally by a factor of 2. So let's take a look at this one, because this one's going to be a little bit different, because of course if it's horizontal, you're going to be working on the inside of the function at the end. So here the input is 0, so when you stretch it by a factor of 2 and you multiply the input by 2, it goes nowhere. So it stays right here. And then the blue point right here, it has a horizontal distance right here of -1. So when you multiply it by 2, it's going to go to -2. So it's going to go right here. And the same thing with the green point right here. It has an input, a horizontal distance if you want, of 1. So when you multiply it by 2, it's going to go right here. And you can see it's exactly what you would think. If you stretch something horizontally, you would think to yourself, and take this case, the graph doesn't get more narrow, it gets wider. And so we connect the dots, and so it looks something like that. Now here's where the trouble comes, when we try to write down the formula. Now what you want to notice is you never changed the outputs. The outputs remained exactly the same. Nothing vertical changed. All right, so we're not working on the outside. Only the input stuff changed. So you're going to work on the inside of the function. And now you stretched it horizontally by a factor of 2. So I want to say you multiply x by 2. But remember, it's the opposite of what you think. So it's the opposite of multiply by 2. And hopefully you say divide by 2. And that's the formula. And actually, a lot of times we'll write like this. Instead of dividing by 2, we'll multiply by 1/2. They're equivalent though, so either way you want to think about it is good. All right, so it's the opposite because we're working on the inside of the function. All right, so now let's look at shrinks. First thing we're going to do here is we're going to shrink vertically by a factor of 2. And I didn't say this in the beginning, but the factor 2 is just sort of random. It could be a factor of 3. You know, we could change this to 4. It could be not a nice number. It could be a 3.5 or something like that. I just chose 2 because it's easy to visualize. All right, so here, what happens when we shrink this vertically by a factor of 2? Well, the height is 0, so it doesn't go anywhere. It stays right where it's at. And then we take this next point here. What happens when we take this point and we shrink it by a factor of 2? So when we shrink it by a factor of 2, the idea is you divide it by 2. And so it's just going to move up here to -1. So it moves up here to -1. Similarly, over here, this point, the green point, if we shrink this vertically by a factor of 2, we just divide the height, which is -2 by 2, and it goes to -1. And we get this point right there. And now we just connect the dots. So it's going to look like this. And then the hard part is really just the formula, but this one's actually pretty nice because what you want to notice is the inputs never changed, only the outputs. And that's because you're working vertically. And so then you're going to work on the outside, so you just write down f of x. And when you work on the outside, you're very happy. You're just going to do exactly what you want it to do. And so if you shrink vertically by a factor of 2, instead of multiplying by 2, you just divide by 2, or multiply by 1/2, right? So you could write it like this if you want f of x divided by 2, or you could write 1/2 of f of x. Most of the time we do something like this, 1/2 of f of x. But that's shrinking vertically by a factor of 2. And so now let's get to the sort of tougher case when you shrink horizontally by a factor of 2. And so the red dot, it's the easy dot. It's not going to move at all because the input is 0. So when you try to shrink 0 by a factor of 2, it winds up right where it started, basically, because 0 divided by 2 is 0. And now we're going to take blue dot, but I'm going to take a different blue dot. I don't want to take this one. I'm going to take the one down here. That way I get a better picture, basically. Over here, horizontally, this is -1. So if I divide it by 2, it's just not that as nice. Whereas down here, the horizontal distance is -2. So you divide it by 2. If you shrink it by a factor of 2, so you divide it by 2, it goes to -1. So it's going to go right there. And we can take the green dot, and we'll also take it down here. So we'll take this point right here. Its horizontal distance is 2, so if you shrink it by a factor of 2, it goes to +1. So it's going to go right here. And again, if you think about what it means to shrink horizontally by a factor of 2, of course this thing is going to get more narrow. It's not going to get wider. And so you connect the dots the best you can with lines, and it looks something like that. And so now again, notice, this case, the outputs never changed. They're exactly the same. So you change the inputs, which means you have to work on the inside of the function. I want to say shrinking horizontally by a factor of 2. I want to say not multiplication, but division, because you're shrinking. So I want to say x over 2, but it's the opposite of what I think. So it's actually 2 times x. Right? Remember, it's always the opposite of what you think. And if you don't believe me, right, or you get confused, and you think it's something else, if you thought for a second this graph here was given to you by f of x over 2, we can test that. Because again, we do have a point. We know if you plug in 1, you have to get out -4. So plug 1 into here, and what do you get? You get 1 over 2. So that's f of 1/2. And you have the graph of f. So f of 1/2, well look, here's 1/2. f of 1/2 is not -4. It says it's -1. So this could not be right. Now come up here and look at this one and say, okay, well, I was wrong. I don't divide by 2, I multiply by 2. So let's check it. Again, if you plug in 1, you need to get out -4. So if you plug in 1, you get f of 2, because 2 times 1 is 2. And over here, f of 2 is -4. So you can see it checks. Right? So it has to be this one. When you work on the outside, everything works how you think it should. When you work on the inside, though, it's the opposite of what you think. Okay, let's talk about our last type of transformation, which is a reflection. All right, so we have 2 types of reflections, reflection about the x-axis and reflection about the y-axis. We're going to start with the x-axis. So here's the x-axis right here. And let's color that in green, because I like green. X is good and y is bad. So here's green. Here's the x-axis right here. What we want to do is reflect about that axis. And so the idea, when you take some points, so this point right here, when you reflect this point about the x-axis, it just stays where it is. If you take that blue point, and we'll go back to our original points here, this point, if you reflect it about the x-axis, it's going to go up here to this point. And then if you take this green point on the other side, and you reflect it about the x-axis, it's going to go up right there. And then we just simply connect the dots. And so when we connect the dots, it looks like this. And like this. And so now what you want to ask yourself is, did you change the inputs or the outputs? And so think for a minute. You know, the red input and output actually are exactly the same. Now the blue input, here and here, they're the same, but the outputs are different. And for the green points, the inputs are the same, because they're both 1, but the outputs are different. So you didn't change the inputs, you changed the outputs. Right? If you change the outputs, what's nice is you can just work on the outside of the original function. Right? So this is the original function over here. So we're just going to work on the outside, and what happened is the things that are negative became positive. So just change the sign. So how do you change the sign on something? Well, change the sign. So right here, you change it. So put a minus. And so minus f of x, this is a reflection about the x-axis. Let's look at the next one. This is a reflection about the y-axis. And so let's draw the y-axis real quick. So I'll do that one in red. So here's the y-axis right here. And what we want to do is we want to reflect about the y-axis now. And so we'll take our red point right here. If we reflect about the y-axis, it stays right where it's at. Our little blue point right here, it's going to reflect about the y, so it's going to go to the other side. So it goes to this side. And our green point basically is going to do exactly the same thing, but go to the other side of the function. So it's going to go over towards the blue point, like that. And we simply connect the dots. And it basically looks like you get the same function back, but it is reflected. So notice, the blue point is no longer on the left-hand side, it's now on the right-hand side. And the green point's no longer on the right-hand side, it's on the left-hand side. So it is the same, but it is a little bit different in a way. And so now how do we write that formula? So again, what you want to realize is, did you work with the outside or the inside? What did you change? And notice, the outsides are the same. The green height here is the green height here. The blue height there is the blue height there. What you changed are the inputs. Over here, the input is -1 for this blue point. Over here, it's +1. So you're going to work on the inside of the function. And just ask yourself what you did. You made the positive input, the negative input over here, and it became positive. Whereas the positive input over here, so the positive input here, became negative. So you're just changing sign. So how do you change the sign of x? You just put a negative in front of it. And so that's a reflection about the y-axis. Okay, and that brings us to trying to put all this stuff together, and that's really the problem we want to solve, which it's not easy to do. It takes a lot of thought as to how these transformations actually work. So when you look at this, you have this, use this graph of f of x, which is right here again. And the transformations to graph this new function, g of x, which is 3 times f of 2x plus 1, then I'll take away 1. So you have basically a series of transformations here. In fact, you have a times 2, a plus 1, a times 3, and a minus 4. So it looks like we have 4 different transformations. So what we want to do is just basically apply one transformation at a time to get sort of this final transformation here. And the rule is this, because you have to start with this transformation. So where do you start? Of course, you do start with the inside, but when you do the inside, sort of like when you plug in a number, you would start here. If you plugged in 5, you wouldn't take away 1 for 5. First, you'd multiply by 2. But when you work on the inside, everything is the opposite of what you think. And not only the opposite of what you think, but the order itself is even opposite. So what do I mean by that? Most students will want to multiply this by 2 first, but even the order should be opposite on the inside. So instead of multiplying by 2 first, we'll actually add the 1. So what we'll do is we'll do a horizontal shift. So let's do a horizontal shift. So we'll call it H shift. And it says +1. So I want to say to the right, but it's on the inside, so it's the opposite. Horizontal shift, and then -1. Right, so we're going to move everything basically to the left 1 spot. So let's just take our points here. So we'll take this point here, and we'll move it here. We'll take this point here, and we'll move it to the left 1. So we'll move it over here. We'll take this point here and move it over 1, so it lines right up with the y-axis. And then we'll simply connect the dots here, so that the dots get connected the best we can. All right, so that's the +1. And now we have the times 2. So the times 2, when I say times 2, I want to think it's a stretch, but it's on the inside. So it's actually a horizontal shrink. It's a horizontal shrink by 2. Right, so by a factor of 2. And so let's do that one. So let's pick some other points here. We pick, let's take this point. Let's take this point right here. And we're going to shrink it horizontally by a factor of 2. So it's going to take it and move it right to 1/2. So we're going to go right here, -1/2. And then we're going to take this point here, and we're going to shrink it by a factor of 2. So it's going to take it to -1. So it's going to go right here. And then we're going to take this point right here, which has 0 input, and it stays right where it's at. So it's going to stay right there. And then we're going to connect those dots. Let's see if I can have if I have a tool on here, maybe I can connect these dots with a little bit better. All right, so connect these dots right here, and then right there. Well, that's nice. All right, so there's the next thing. All right, so Thank goodness, we're done with the inside. So that's finished. We don't have to worry about that thing anymore. Now we're on to the outside. Now the outside's a lot easier. So the outside, you have times 3. So that's a vertical stretch. So vertical stretch by a factor of 3. So by a factor of 3. So we're going to take this dot right here, which has vertical height 0, and it stays right where it's at. We're going to take this height right here, which is -2, and we're going to multiply it by 3, so it's going to go down to -6. So it's going to go down right there. And then we'll take the point on the right here, which also has height -2, and stretch it vertically by a factor of 3, so it's going to take it right down there. And then we can just connect those dots. We can use this nice little tool here. Point there, and point there. Okay, now we're going to subtract 1. Right? So if we subtract 1, we don't, and let's change this because I don't like the -1. I'm going to change this. Oh, let's keep the -1, I guess. So I'll keep the -1. So the -1 is a vertical shift. So it's a vertical shift. And this is -1 since it's on the outside, so it's down 1. So what's going to happen now? Let's take a look. So we'll take this point and we'll shift it down 1. So this point shifts down 1. You can even label it if you want. That's the point. It'll be -1/2, comma, -1. And then these points here, the one reason I wanted to change the transformation is because it's going to go off the screen, but that's okay. We can just, we'll just move it down with us, right? So this point here is going to go from -6 down to -7 right here. Right? So it's going to go from -6 down here to -7. We'll scroll down a little bit. And this point right here is going to go down to -7. So this is actually the point on the left. This is -1, comma, -7. And this point is 0, comma, -7. And then, of course, we can connect the dots here then with this little tool. And in a second, we're going to check our work because that was a lot to do. But we're basically just kind of tracing points. So let's check our work. So how can we check our work on here to see if we did it right? Well, we know that our new graph g of x, that's what this is. We didn't need this second one, so we can scratch it out. So this is our new graph g of x. So we know if you plug in -1/2, you're supposed to get out -1. So let's check it. So what's g of -1/2? And so to figure that out, what we do is we come over here and we plug it into the formula. So that's g of x. So it should be 3, and then times f of, and then you have 2 times your x, and our x is -1/2. So 2 times that, and then plus 1, and then take away 1 from everything. So this will be equal to 3 times f of 2 times -1/2 is just a -1 plus 1 minus 1. And then that's equal to 3 f of, and then what's f of what? -1 plus 1 is 0 minus 1. And so then what's f of 0? Well, f of 0, remember, this is the original graph, f of x. If you plug in 0, you get out 0. That's a point 0, 0. And so then, what do we have here? We have 3 times 0 minus 1, which equals a -1. Oh, it checks. If you plug in -1/2, you do get out -1. And you can also check it with these other 2 points. All right, so let's review real fast what we did today. So we talked about some basic graphs and formulas that you should be aware of. Then we talked about 4 different types of transformations. We talked about these vertical sort of shifts, which are real sort of simple ideas. A vertical shift up by A looks like this. A vertical shift down by A looks like this. Then we talked about stretches. Oh, and then horizontal shifts. A horizontal shift to the right is the opposite of what you think, so it looks like this. The horizontal shift to the left looks like that. And then for stretches, you have vertical stretches and horizontal stretches. So a vertical stretch, say by a factor A, looks like that, A times f of x. Whereas a horizontal stretch looks a little bit different, so by a factor of a. I want to say it's a times x, but it's the opposite. So it looks like this, 1 over a times x. So that's a horizontal stretch by a factor of a. And then we have the shrinks. And so a vertical shrink by a factor of a looks like this, 1 over a f of x. It gets smaller. And then a horizontal shrink, I want to say divide by a2, but it's the opposite. It's a times x. And then for the reflections, of course, the reflection across the x-axis. So what happens across the x-axis is you're working on the outside. So this is a reflection across the x-axis. And of course, this is then a reflection across the y-axis. And then we want to put all these things together. So remember, when you put them all together, on the inside, everything's opposite, even the order of operations.